And they found that things in nature often fall into this normal distribution. If we look at the height of trees in a forest, if we look at 10,000 trees, there will be an average height of trees, and there will be some sort of distribution. And the average, we call the mean, will typically be the most frequent. Well, if it's normally distributed, it will be the most frequent, and there will be deviation from that. There'll be really, really tall trees, there'll be really, really short trees. If you were to look at another group of trees, maybe in another country, another continent, and you would look at how does that data distribute, you would find an average for the height of the trees, and you would also find a normal distribution, unless there was some sort of bias going on. And we talked about various things that might be going on with this fictitious town we looked at last time. We said, what if the mean income and median income are significantly different? And we were able to ascertain certain things based on those examples. And we were particularly able to determine that there was something skewing the data. It was either positively skewed or negatively skewed. And that was interesting to us as we examined the data. But if we step back from that and say, just assume complete randomness, then things will often fall into this normal distribution. And you can do experiments yourself if you're so inclined. If you were to conduct an experiment where you were to take a feather and drop it on the floor and mark where it landed each and every time, most of the time that feather would probably land directly below where you drop it from. But there would be natural deviation based on the wind, based on, what else? I don't know what else there would be deviation based on. But it would fall into a normal distribution if you repeated that over and over again. As long as there weren't some bias where you were like twisting your hand a certain way, or you were leaving a window open so everything blew in one direction. Over and over again, you could find that normal distribution. And if someone else were to repeat that same experiment somewhere else, in a different country, on a different continent, they would find the same normal distribution. Or for that, another country, another continent, for that matter, I don't know, an alien species 100 million light years away, if they were doing an experiment like this, it would fall into a normal distribution. Because this is the way randomness is distributed. And this is what mathematicians discovered. It didn't have to look like this. We mentioned earlier, or last time, it could look, it might look like the frequency might be here, and you might have a linear relationship. Right? It might look something like that. Possible. What are we to know if it weren't? But it didn't. It looked like this when mathematicians discovered it. Or it might look sort of like a upside down U, where we have some variation, but we don't have extreme variation on either side. So, normal distribution. We found that things fall into this normal distribution, and this is remarkable, and this is very, very helpful to us. Because we know that as things are randomly distributed, we can quantify this data. We can determine how likely it is to have certain outcomes. And we talked about this idea of a z-score based on the percentages under a normal distribution. And one thing I didn't mention last time, but you may have seen when you were reading in your textbook, was there is standard percentage within one standard deviation of the mean in a normal distribution, and there is also a percentage of the data that will always be within 2 standard deviations of the mean and 3 standard deviations. Did anyone get that in the homework? Can anyone tell me, in a normal distribution, how much of the data will be within 1 standard deviation of the mean? You're on the right track. That's not 1. That is actually 3 standard deviations. It's 99.7. So within 1 standard deviation of the mean, yes, I'm hearing the right answer. 68.3?
Yeah.
Yes, okay. So 1 standard deviation, 68.3. All right, so everybody who conducts this experiment, if it falls into a normal distribution, 68.3 of the trials of the points of data will be within one standard deviation. Again, I use the cheesy example. If you're doing this here, if you're doing an experiment here, you're doing it in another continent, aliens were doing it 100 million light years away, it would fall into the normal distribution. All the data would be within 68. Of all the data, 68.3% would be within one standard deviation. And what percentage of the data falls within 2 standard deviations? So they fire up the answer there for me, and I will draw.
95.5.
Yes, that's correct. How am I going to notate this? Okay, so this is 1 standard deviation, 68.3, 2 standard deviations, 95.5. Okay, and Phil, within 3 standard deviations
99.9
is 99.7, right?
7.
Yes. Okay. Okay. All right. So we know those figures as a rule of thumb. We could also calculate any amount in between that. We could say, well, what falls in, how many standard deviations fall in 45% of the, collect 45% of the data. And we can break this down using our z-score. Can someone remind us how the z-score works and what it tells us? Phil.
You calculate the z-score based on that formula and on the chart, and it gives you a percentile. Depending on, if we're saying it's less than or equal to or greater than or equal to a certain mean.
Okay. Yes. Yeah.
You know, you're either going to say it's below, people are below the percentile or above it, based on how the question's asked.
Okay, so we'll look at this above the mean or below the mean. So you look at this x is the sample statistic. We used the example of male height last time. And we said, well, the average is, I forget what we said, 5'8"? Yeah, and we said if Michael Jordan is 6'5", so we have 6'5" here, 5'8" here. So we're going to get a positive number in the numerator, and we're going to divide that by the standard deviation. So this z-score is going to tell us how many standard deviations Michael Jordan is above the mean. And he was, I think, 2.2 standard deviations above the mean. So we would put him somewhere right about here. And then we used an example for someone else who was a little bit shorter, and we found that I forget who it was, Rich was I maybe 1 standard deviation below the mean, something like that, or part of 1 standard deviation below the mean. All right, so that is what we did last time. I think tonight we are going to take that a little bit further, and we're going to think about sampling. If we were to sample, we would want some information about a population. Suppose we have a population of residents in a fictitious town in New Jersey, and we want to know the average income in that town. Now, maybe it's a little difficult for us to survey every single person. That might be ideal, but it's difficult, it's challenging. So we want to sample. We want to take some random samples and see what we can learn about the mean, the average income in that town. And we talked a little bit about random sampling last time, and we talked about why that was important. Can someone refresh us? What is random sampling, and why is that important? So, random sampling, if we're going to calculate the average income in this town in New Jersey, are we going to stand at a bus stop and ask everyone we see, how much do you make, how much do you make? And when we get to, say, 50 people, say we've got our sample of 50 people? No. Why is that not going to give us an accurate sample.
There's a bias there because it's only the people that ride the bus.
Exactly.
Statistically are probably
Exactly.
lower.
Similarly, we're not going to go to the golf course and say, how much do you make, how much do you make, how much do you make? We're going to conduct some sort of sample where each person in that town has an equal chance of being selected for this survey. And we need to do it in a way that ensures that. And if we sample randomly, we can make some assumptions which we'll get to in a minute. So, we are going to conduct some random samples, and we are going to come up with a sample mean. I mentioned last time that this little mu figure, right, we're going to call that the population mean. Population mean. All right, and when we take a sample, we're going to use this symbol, x with a bar on top of it. It's going to be our sample mean. Sample mean. Okay. So we're conducting samples in this town in New Jersey. Say we're asking 30 people, what is your average salary? And we're going to get some sort of number. We're going to have an X bar number. Suppose we get X bar of 59K. All right? And we find, of the 30 people that we sampled, the average salary was $59,000. And I'll introduce one little notation also. The number of people in our sample we'll call little n, 30 people. The lowercase n is the number of people in our sample. And I think we went over last time that a capital N is the number of people in the whole population. But tonight we're using this little n, and we're going to say we're sampling 30 people, and we're going to get some sort of number. Okay, so I have a plan of how I want to present this. I'm going to go slowly, and we'll go over it again and again as necessary. But I want you to start thinking about as we sample, and if we were to do this continuously, what sort of frequency distribution might our sample means fall into? So I just gave an example of how we did it one time, and we came up with 59K. All right, so this is our first attempt, 59K. Suppose we do it again. All right, x2, we come up with 61K. All right, suppose we do it a third time. X bar 3, and we come up with, 55K. So, if we were to do this in a simple random sample fashion, over and over again, don't blurt out the answer if you know it, just think it through. If we were to do this over and over again, what sort of frequency distribution might our sample means fall into? So let's call this our sampling distribution of the sample mean. Jot that down. Sampling distribution of the sample mean. So what that means is we're going to have a quantity. I mentioned 3 examples. First time we do it, we get 59,000. Second time we do it, we get 61. Third time we get 55. All right, those would be on the horizontal axis. And then the frequency. Now, we would chart those. Like, for example, we have 59, 60, and 55. We might put the 59 here, the 61, or the 59 here, the 61 here, and the 55 here. And we do this over and over again. Just theoretically, if we did it over and over again. The question we're ruminating on right now is if I were to plot, say, 1,000 different attempts at finding the sample mean, what sort of frequency distribution would they fall into? What would it look like? But don't blurt out the answer if you know, just think. Smile at me if you know. Alright, I see 1 or 2 smiles. Now, I'll give you a couple options. Well, might it look something like this? That might be one possibility. Might it look something like this? This we talked about a little bit last time. This is a uniform distribution. So this is, between, say, 20,000 and 95,000, there's an equal number of people. All right, if we are sampling, we might find an equal number of 59Ks, an equal number of 61Ks. Now again, just where we are, we're talking about going out, conducting a simple random sample of 30 people, and we want to know what sort of frequency distribution that data is going to fall into if we do it over and over again. I showed you this is one possible option. Showed you this is another possible option. What else? Maybe like this. Maybe the upside down U. And suppose these go all the way down to the bottom. So we have maybe some sort of mean, which we get most of the time. And we have variations from that. But we don't have any extreme outliers in our mean. Okay. So again, question we're still ruminating on. If we conduct a sample over and over again, and we put this on a frequency distribution, and we call it the sampling distribution of the sample means. What sort of distribution will this fall into? Does anyone know? Normal distribution. What do you think, Dan Ryan? Cumulative? No, the correct answer is normal distribution. Because we're doing this in a random sample over and over again. And as long as we're not biased in the way we're collecting this data, it is going to fall into a normal distribution. Sampling distribution of the sample mean will be distributed normally. There's going to be some sort of income figure that we're going to get the most, the highest number of times. Not most of the time, mind you, not over 50% of the time. There's going to be some sort of symbol. And every once in a while, we're going to get a bunch of poor people in this sample, and they're going to drag our sample mean a little bit lower. Every once in a while, we're going to have a higher proportion of rich people. They're going to push the mean a little bit higher. And every once in a while, we're going to have some extreme outliers. Suppose this is our job. We do samples. We do the same sample every day, over and over again. And some days we'll come out and look, wow, I just ran into 30 really rich people. Did I do that right? Yeah, I followed the simple random sample. That only happens once a year when I do this sampling. Or conversely, a bunch of really, really poor people. So this sampling distribution of the sample mean falls into a normal distribution. Does that make sense to everyone? So what that allows us to do, it allows us to guess or estimate at how accurate our sample mean is. So here we are, we've got this experiment where we're conducting samples each and every day, all day, in this town in New Jersey. Question I have for you all, so when we pull this sample mean, what percentage of the time will we get a sample mean that is within one standard deviation of our mean of our sampling distribution of the sample mean? Amanda, what? 68.3%. Okay, so we've done this Emeka 10,000 times. And we've collected a sample 10,000 times, and we've plotted those. Like, what was our mean? What was the frequency of it? And we just agreed that it's going to fall into a normal distribution. Because it falls into a normal distribution, it allows us to estimate, make assumptions about how accurate that is. So there are three important takeaways from the fact. All right. Three important takeaways from the sampling distribution of the sample mean. One, if, I didn't mention this to you, but if our sample size is large enough, and statisticians like to say above 30 in this example. So if little n is greater than or equal to 30, it is normal. All right, so the whole thing I took you through, it's going to fall into a normal distribution. The sampling distribution of the sample mean, that is normal if n is greater than 30. 2. The mean will equal the population mean. So the actual population mean of salaries in this town, suppose it is 57,000. When we do this sampling over and over again, the most common sample mean we're going to get is 57,000. Makes sense, right? If we're doing this in a random fashion, we would get the right answer more often than any other answer. 3, the standard deviation of the sample mean, which we will notate with the standard deviation sign, and we'll put a little X bar below it, or X bar below the standard deviation, is something that we can quantify. And by quantify, I mean we can base it on the population standard deviation. And let me explain that before I write that notation down. What happens to the standard deviation in this sampling distribution of the sample mean is it gets smaller. It gets smaller than the population standard deviation. So, say for example, this is I'm going to do it this way. Okay. I'm going to call this the population. And we don't know exactly what the distribution is going to be like. It may be skewed, may not be skewed. But it's going to have a certain standard deviation. This graph is going to encompass everyone in that town. Their income if it's very low, their income if it's very large. But when we do this sampling over and over again, we're looking for just one number. We're looking for the average. And we may come up with the average of 59, 61, 62. We're just looking at the average. So what happens is the standard deviation as we go from the population to the sampling distribution and the sample mean gets smaller. Does that make sense? It gets smaller because we're just looking for one number, the average. Yeah, we're just saying, what's the average? What's the average? What's the average? All right? And that's going to center around the mean of the population. And the standard deviation is going to be smaller. It's going to be the standard deviation divided by the square root of n. So the standard deviation of the sample mean is the standard deviation of the population divided by the square root of the number of people in our sample. And as you can see, as you might guess, the bigger n gets, the more people we sample, the smaller the standard deviation is. Does that make sense? Okay. I'm going to revisit the same concept. I just realized there's one thing I didn't really stress, so I want to just give you a couple of examples, and the answer will be the same thing we've been talking about for 15 minutes, so don't think I'm moving on to something new. I'm just going to give you a different way to look at it. I'm going to give you a few examples of population distribution. So we'll call these population. All right, population. So suppose, remember we talked about some skewedness in our fictitious town. Suppose I have one that is a little positively skewed. All right, suppose I have a town, a weird town, that has a uniform distribution. And suppose I have maybe a different town that kind of has a bimodal distribution. So, I've got these three towns, and my job is to go into each of these three towns and take a sample to find the mean income in each town. And I'm going to take a sample. I'm going to have some information, an understanding of statistics that's going to help me. Let me change titles on you here. All right, now suppose I take sample means from all of these, and I want to put them into a frequency distribution. What is the frequency distribution for all three of these going to look like? Micah?
That's a normal distribution.
It's going to look normal. It's going to look normal. This one, well, let's start with the uniform distribution one. Right? There is a center to this distribution. Right? There's going to be the average if you add them all up. So if I take a random cross-section of all of these people, then it's going to gravitate towards the center. Sometimes I'm going to hit a bunch of poor people in my survey. Sometimes I'm going to hit a bunch of really rich people in my survey. But that is going to move towards a normal distribution. I told you I was changing titles here. So I'm now calling this the sampling distribution of the sample mean. Distribution. Sample mean. Okay, so I have a uniform distribution in the town, a very weird town where only a certain number of people have each level of income. I sample that, I do it over and over again, it would fall into a normal distribution. How about this one, where I have a positive skew, where I have a few really super rich people who are pulling the mean higher? If I were to take a sample of the people in that town, and I were to do it over and over again and put it into a frequency distribution, what would the frequency distribution of the sample means for this town look like? Normally distributed. Well, wait, but what about the higher mean and the higher median? Doesn't matter, because there is some mean, and I'm looking at that mean each and every time. Sometimes I'm going to hit it right on, Sometimes I'm going to get a little higher, sometimes I'm going to get a little lower. It doesn't take into account the outliers the same way. Same thing for this funny-looking bimodal town. All right, we've got a bunch of people who work for the factory, then maybe a bunch of people who work for the university, something like that. Well, this still has a mean, and we might call it like right here. This might be the mean. That's what we're going to get most of the time. Not most of the time, more often than any other. And that's going to fall into a normal distribution. So, falls into a normal distribution is one of the properties of the sampling distribution of the sample mean. The mean of the sampling distribution of the sample mean is the population mean. This mu is the population mean. And the standard deviation of the sampling distribution of the sample mean is the standard deviation of the population divided by the square root of n. I want to make sure everyone's comfortable with this language right here before we move on. Sampling distribution of the sample mean. You just need to say it a few times. You're comfortable with what it means so it doesn't scare you. It shouldn't scare you now, and we'll revisit this in different ways throughout the quarter. Sampling distribution of the sample mean. Simply means if we were to theoretically take samples over and over and over again, what would the sample mean? And we can notate the sample mean, you can recall, with this x bar. X with a little hat on it. Or x bar. X bar. So we're going to have a bunch of x bars. Sampling distribution of the sample mean. Okay. So, here we are. We've taken one of these samples of 30 folks. And the next question we want to ask ourselves is, what is the probability that that sample is accurate? I want to ask you, again, I asked you this question earlier. Just think about it again. What is the probability that this sample mean we've taken is within one standard deviation of the true population mean? %68.3%. So the chances of the mean we just collected being within one standard deviation of the true population mean, 68%. What is the probability of that sample mean being within two standard deviations of the true population mean? 5.5. What is the probability of that sample mean being within three standard deviations? 99.6. Or 99.7, excuse me. So, this brings us to what we call confidence intervals. So if we take a simple random sample of at least 30 people, we can make assumptions about the normality of the sampling distribution of the sample mean, and we can say we are 95.5% confident that that number is within two standard deviations of the mean. And we can quantify the standard deviation, just the same way you all quantified standard deviation for the quiz. You said, all right, the average is this, the mean is this, and the standard deviation is this. So suppose we find, the mean to be 59K. All right, and then we suppose we find the standard deviation to be 2K. All right, so this is the mean we get on this particular day, or this particular hour of this particular day. We find the mean to be 59K, and we find the standard deviation to be 2K. We could say we are 95.5% confident that the true population mean is between what and what? like to write confidence intervals with these brackets. Actually, let me do it this way first. Before I get to the actual confidence intervals, I'm going to say that we are 95.5% confident that the true population mean is 59,000 plus or minus 4K. 59K plus or minus 4K. And in this case, we're calling the 4K is our margin of error. You all have heard pollsters on the news talking about percentage of people that like this or don't like this. And they will often tell you the margin of error, 3 percentage points, margin of error, 4,000. In this quick example, the margin of error is 4K. And if we were to calculate that out for a confidence interval, we would subtract 4,000 from 59, and we would add 4,000 to 59. And we would say our confidence interval is 55 to 63. So we are 95.5% confident that the true population mean of average income in this town is between 55 and 63,000. Does that make sense? Everybody with me? All right, fantastic. Let's see, what did I have next? Wanted to turn to a couple problems. All right. Let me give you an example before we open the textbook. Suppose I were to tell you that I am doing a survey of the average cost of an MBA program. And I do a simple random survey, 30 people or more. I do it with good statistical principles. And I come up with a sample mean of 43,000. So, I've got some real estate over here. So, we're going to notate the sample mean with this X bar, 43,000. All right, this is the cost of an MBA program. And I'm also going to tell you that I know the standard deviation. We'll say the standard deviation of my sampling distribution. So standard deviation of my sampling distribution, not the standard deviation of the population, is 2,000. And you give me the 95.5% confidence interval for the true population mean for the cost of an MBA program. 95.5% confidence interval for the true population mean for the cost of an MBA program. All right, does everyone have an answer? All right. What is the confidence interval? What is the 95.5% confidence interval for the true population mean? So I'm going to take this first. Selena. Selena says 41 to 45. 45. Okay, so we're at a 95.5% confidence. Is this correct? This is not correct. Okay. What is this, Lena? 39 to 47. Alright, we could write out the confidence interval like that. Or you could also say 43K. 43K plus or minus what?
4K.
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 Outstanding. All right, and this 4K we call the margin of error for this sample. All right, let's take a look at a couple problems in your book and work through that. So if you have your textbook, please pull that out. Let's look at page 248, and let's look at exercise 7.4. Okay. So, page 248, exercise 7.4. In this example, for a random sample, 60 new BMW 5281 or 80i automobiles sold last year. The average time cars stayed on the lot before they were sold was 97 days. All right, so we're taking a random sample of 60 of these BMWs, and we're determining after they've been sold, and we're trying to ascertain the average time that they remain on the lot. 97 days. Build a 95% confidence interval estimate of the average time spent on the lot before the sale of the entire population of BMWs sold last year. And we're given in this example that the standard deviation of the population is known to be 22 days. Now I need to tell you two things before we move forward in this problem. We know if we were asked for the 95.5% confidence interval, we would use 2 standard deviations. But we're not. We're asked for just 95%. So we're going to use a little bit less than 2 standard deviations. And for now, I just want to tell you what that is. But once we get comfortable with it, you'll crack open the z-table, and you'll find the exact answer that way. But anytime you're asked for 95% confidence, again, it's a little bit less than 2 standard deviations. It's 1.96 standard deviations. So that's the first thing I want to tell you. And the second thing I want to tell you is remind you that we are given the population standard deviation, and now we need to calculate the standard deviation for the sampling distribution of the sample mean. And remember how I mentioned that the standard deviation of this is smaller, because we're just looking for one number each time. It's not as affected by the outliers. It's smaller, and it's calculated standard deviation of the entire population divided by the square root of n. So, for this example, we know, yes, Lee. Oh, what, 248? Page 248, exercise 7.4. All right, so let's see. So we've got, let me make some space here. Okay. All right. So, X bar. What does that mean again? Sample mean. And what does the sample mean in this case? 97. Excellent. All right. Let me throw some other terms just to make sure we're clear. This mu, this little u, what is that? Mean. Mean, what kind of mean?
Population.
Population mean, exactly. All right. Population mean. Alright, and we're wondering what that is. Alright, this little squiggly thing, sigma, the O with a hat on it, what is that?
Standard.
That's the standard deviation of what?
Population.
Population. Alright, so standard deviation of the population. Alright, I'll just say it, and we're given that in this example, right? What is it? 22. Alright? And then How about this thing? The same standard deviation symbol with the X and the hat. What is that? What's it called?
Standard deviation of the sample mean.
Standard deviation of the sample mean. All right, it's the standard deviation of this, or the standard deviation of this, and it's smaller than the standard deviation of the actual mean. And we calculate the standard deviation of the sample mean how? What amount? No.
The standard deviation divided by the root of.
Yes. Yes. The standard deviation of the population, 22, divided by the square root of n, which is 22. Wait a minute, what happened? Oh, little n. Forgot to do little n. Little n is the number of people in the sample. Number of samples taken. And what was the number in this example? How much? What color?
60.
60. Okay, 60. All right, divided by the square root of 60. All right. And what do we get when we crank that out?
2.8402.
All right, 2.84. So, our estimate for the true population mean is going to be our sample mean of 97. 97 plus or minus some number of these standard deviations. And if our confidence interval was 95.5%, we would take 2 of these, but it's a little less than that. It's just 95%. So we multiply this standard deviation by how much?
1.96.
1.96 times 2.84. Someone want to crank that out? 1.96 times 2.84. 97 plus or minus
5.57.
5.57. Okay. We could, and is that correct? Did we get that right?
Yeah.
Okay, fantastic. All right. We could leave it like that if it's reasonable to leave it like that. If we're asked to give the actual confidence interval, what would the numbers be? The actual numbers in the confidence interval. 91.43, 102.5, call it 6. 102.57, leave it 57. Okay, that makes sense. And how do we, before we move on, how do we state this? I were to ask you, what does this mean? How are you going to articulate this to me?
The 95% confidence interval is that.
Okay, you're on the right track. Well, there's nothing wrong with what you said. How about say it? I'm X% confident, and then continue the statement. Try it.
95%.
Oh, I'm sorry.
I'm 95%.
You are 95% confident.
Yeah, confident that the confidence interval, the population mean.
That the true population mean
Population mean
is what?
97,000 plus or minus 5.57.
Yes, yes. You could also say I'm 95% confident that the true population mean is between 91.43 and 102.57. Any questions on that? All right, let's try a couple of those.
That's a good question.
Yes, Phil.
Sorry, I know I sent that out, so I missed it. That 1.96 is that the 1 plus the 95.5?
Okay, someone will explain the 1.96 to Phil? Rich. What's your name again? I'm sorry?
Randy.
Randy. Got it. Sorry.
That's the 95%. 2.5.
Okay, yeah, I think you're on the.
It's the
You're
one,
on,
is it the 1 plus that percentile?
Yeah, that's everything you said was correct. Can someone else say it in a little more succinct fashion? What is the 1.96? Diana.
Since it was 95%, instead of 95.5, it was a little bit less than 2 standard deviations, so it was 1.96. Instead of 2.
Yes. So we said earlier, Phil, that 95.5% of the data is within 2 standard deviations. So we could actually have written this out. It would have been a little funny. We could have said 95% is within 1.96 standard deviations. So we were asked for 95%, so we used 1.96. And I just gave you all that figure because I didn't want to confuse us by going back and forth to the z table, which we will do momentarily. All right, let's do that same page, 248. Let's take a look at number 20. Number 20. What I'd like to do is just give you a minute to try to absorb this and do that on your own. And we'll see if we can check back in and see how you're feeling with it.
You said page number?
248, number 20. These Turnip landscape. All right, let's come back together. So we're trying to find out how much time these teenagers spend online. We can't ask every single teenager, so we take a sample. How many teenagers do we sample?
754.
754. All right, and what did we come up with the amount of time they spend online? 8.2 hours. 8.2. All right, and we're going to notate that with the X bar. Now, we know something about the population standard deviation. We're going to talk about how we might know that and what we do if we don't know that. But for now, we are given population standard deviation of what? 2.6. And we are asked to find the 95% confidence interval for the average amount of time these teenagers spend online. So what's the first thing we need to do?
Standard deviation of the sample mean.
Yes, that's what I would do. I would calculate the standard deviation of the sampling distribution of the sample mean. And we notate that with this funny looking O, and then we put the X bar right beside it. Alright, and we know we can calculate that by taking the standard deviation of the population, 2.6, divided by the square root of the number in our sample, 754. And what does that equal?
0.095.
0.95?
0.095.
0.095.
Yeah.
Point 0.91. Is that right? Whatever.
0.0.
0.095. Is that right? Okay. So now we want to build, so this is the standard deviation of the sampling distribution and sample mean. So how do we now go about building our 95% confidence interval? Diana?
95%
Times 0.095, and we're taking our sample mean of 8.2 plus or minus 1.96 times 0.095. That gives us 8. Down on one knee here. 8.2 plus or minus what?
19.
0.19?
Yeah,
0.19? Is that right? What you all got? Yes. 1.96. We were asked to go 95% confidence interval, and we know if we look at the Z table, we could verify this that 95% of the data is within 1.96 standard deviations of the mean. Well, you'll look at the Z table. If you'll just remember 1.96. There's a number of them that you'll just remember. But if you're asked for something specific, you'll look at the Z table and say, what contains 95% of the data, or what contains 80% of the data? We know that because this sampling distribution of the sample mean is normally distributed. We know that because that's just a law of nature that mathematicians discovered. And I gave the silly example of people in different continents would come up with the same normal distribution. Alien creatures 100 light years away, if they were intelligent, would come up with the same standard deviation normal distribution. And we know that as long as this sample is done in a non-biased fashion, that 95% of the data will be within 1.96 standard deviations of the mean. And we were asking this problem to build a 95% confidence interval, and that's what we came up with. Okay. All right, let's try another one, just like it. And we're going to get a little bit more nuanced with this one, but we're going to do number 22 on the next page, page 249. Let's do it the same way. Start with A. A is what you've already done. You already know how to do. And then when we get to B, we're going to have to crack open the Z-score table. So start with 22A on page 249.
1.96 is the 95%.
All right, let's come back together. So for this problem, we want to find an average teacher salary. Can't ask every teacher. We take a sample. How many teachers do we sample? How many?
200.
200. Fair enough. All right, and what did we get for our sample mean?
60,000.
How much? 68,000?
No, 60,583.
60,500 what? 83. Okay, 60,583. So before we go on, let's just do a quick temperature check here. We've just taken a random sample of all these teachers. How confident might we be that this 60,583 is close to the true population mean? The true average salary for everyone?
95%.
Okay. So we have to speak in tandem with the 95% and the confidence intervals. So we might say the three statements we started class with. We might say we're 68.3% confident of what? That this sample mean is within one standard deviation of the true mean. Notice I stand up on toes when I say true. The true mean. All right. We could also say we are 95.5% confident of what?
It's between two standard deviation of the
That
true.
this sample mean is within two standard deviations. Right, we're 95% confident that the true population mean is within two standard deviations of this. And so on, 3 and 4. Okay. What else do we know in this problem?
6,800.
How much? 6,800 is the standard deviation for the population, and we need to construct the standard deviation for the sampling distribution of the sample mean. And we construct that by taking the 6,800 divided by the square root of n, which is 200, and that equals what?
480.
4 what?
480.
0.9, are we good with 0.9? Is that
Maybe 0.8. It was 0.83.
Yeah.
0.83? Okay. 0.8. Okay. So we are asked, in this case, to construct a 95% confidence interval. So we're going to start with our point estimate, our sample mean of 65.83 plus or minus how much?
942.
940.8. We need to multiply this by something, right? Times 1.96. And what do we get with this chunk here? What's our margin of error?
942.
942.4. Okay. So 60,583 plus or minus our margin of error, 942.4. Okay, good. You feel comfortable with that?
Yeah.
Next question. So this is our 95% confidence. Confidence. Part B asked us for 99% confidence. All right, so question is, what do we multiply our standard deviation by for 99% confidence? In the previous example of 95, it was 1.96. If I had asked you for 95.5, you would have multiplied it by 2. If I were to ask you for 99.7, you would multiply it by 3. Unfortunately, I'm not asking you for any of those. I'm now asking you for 99%. So what we need to do at this point is crack open the z-table. We need to figure out what z-score we multiply our standard deviation by to give us the 99% confidence. Before we do that, let's do that process with the previous question, the 95%. We already know the answer is 1.96, but let's just, our first time looking at the z-table with this calculation, let's solve that problem by cracking open the z-score table. So, let's go ahead and do that. Let's go ahead and turn to the z-table in the back of your book. All right. So, point out to you, in this example, with the two standard all the data being within 95.5% of the data being within 2 standard deviations, what that means is some of the data is a little bit high, some of the data is lower than that. So, how much of the data is greater than 2 standard deviations above the mean in this example here, where I'm telling you 95.5% is within 2. My question to you now is, what percentage is greater than 2? What percentage is in this little spot right here?
0.2?
0.2?
No, sorry.
Well, I'll give you a hint. So we've got 95% in this section. So the most that could possibly be here would be 4.5.
Yeah.
Right? Is that how much is there?
No,
No,
because it's distributed sites.
Because half of it is above,
Yeah.
and half of it is below. So how much is above?
2.25.
Yeah, whatever. 4.5 divided by 2. So if we were to do the same thing with the 95%, how much of the data would be above, and how much would be below? So we've got 9. We want to know how. We've got the same chunk for 95%. I'll tell you the answer because I don't want to confuse you. 2.5% would be above. 2.5% would be below. So we.
So total. So the 5% would be divided among both sides.
Yes. It could be extremely high. It could be extremely low. There's 2.5% of the time when we conduct this sampling, where we're going to bump into 30 really rich people who are going to give us a sample mean that is higher than 2% or than 2 standard deviations above the mean. 2.5% of the time, we're going to bump into a bunch of really poor people who are going to give us a sample mean below. So, where we are now is we're looking at a 95% confidence interval, and I'm going to ask you, what z-score do we use for a 95% confidence interval? And the answer we know is going to be 1.96. What I want to do now is just open up the z-score table and get you comfortable with finding that 1.96. All right, so if you open your textbook to page 568, you can either look at page 568 on the negative side or 569 on the positive side. Let's start by looking at the negative side. 568. So we're looking for those numbers in the center. And we're going to look for an area probability of 2.5%, which is 0.0025. So in this middle section, we want to find the 0.0025 number. All right, if you have your textbook, just find it. Find point, or excuse me, not 0.00, 0.025. My bad. Okay, so let me write that down. Let's see, I'll write that down. So 2.5% is the same as 0.025.
So the negative first, right?
Yeah, so we're looking at the negative, the 568. So you're looking for the number in here that says 0.025. Does everyone have it?
Yeah.
Put your finger on it. All right, what is the z-score for that area of probability?
Negative 1.96.
Negative 1.96. Then if you look at the top, it's telling you that the area below a negative 1.96 z-score is 2.5% of the data. So if we were to ask, build me the 95% confidence interval, I would know, all right, 95% confidence interval. That means I'm going to be 95% confident that this sample mean, it represents the true population mean. But there's a 5% chance that it doesn't. There's a 2.5% chance that the population mean could be really low, 2.5% chance that the true population mean could be really, really high. So we turned open our page to the z-table. We found the 2.5 on the negative side. And we found the z-score for that level of confidence to be 1.96. Let's do the same thing on the positive side, page 569. You can see that the way this table is set up is it's going to tell you the area or probability below a z-score that extreme. So on the positive side, it's going to tell you 1 minus 2.5%, which is 97.5% of the data, is less extreme if you were to pick that z-score. So on the positive side, page 569, you're going to look for 0.9725. So everybody on page 569, look for 0.9725 and put your finger on that.
0.975.
0.975, sorry. 0.9, yes, 975. Okay, so everyone found it? Put your finger on it? 0.975. Are you trying to find it on the cell phone? All right, I'll show you. You can look up here, Mecca. So,
Oh, okay.
all right, so I'm looking up here. I see it. What is the z-score associated? For what z-score will 97.5% of the data be less extreme than? What's the z-score then? 1.96. So, if you were asked the question, build the 95% confidence interval, you know that 5% of the data would not be within that confidence interval. There's a 5% chance that this sample mean is way off. 2.5% chance is too low, 2.5% chance is too high. You will see the z-scores in that fashion. You look on the negative side, we said, well, 2.5% on the low side. Look on the positive side, 2.5% on the high side, and we came up with 1.96. Does that make sense to everyone? Yes? Now it does? Okay. And I see nods. A little bit hesitant on the nods, but at least I'm seeing nods. So next question. Suppose we want to build a 99% confidence interval. What do we need to do with our z table in this case? Let me set it up here. Let me just draw a picture. So I'm asking you, I'm saying, I want to encompass 99% of the data. Okay, so I want a z-score that's going to encompass 99% of the data. Okay, so every single time you do this sampling technique, of all those times put together in a sampling distribution of the sample mean, 99% of the time you are going to be within what and what. And you need a z-score associated with that. And then you're going to multiply that z-score times the figures that you come up with. So what that means is 1/2 of 1% of the time, right, you're going to be wrong in this direction. 1/2 of 1% of the time, you're going to be wrong in the low direction. So this is 0.5%. 0.5% or 0.005. All right, and on the other side, we're looking for 0.005 as well. And I want to find the z-score, which is going to give us that wide of a confidence interval. So when you open up your textbook, page 568, what am I looking for on this negative side? I'm looking in the center. What number am I looking for? 0.01? You're not looking for 0.01 because remember, you could be wrong either on the negative side or the positive side. So half of that chance of error is in the negative, half of that chance of error is in the positive. Sure, start with negative. What am I looking for? What's your name, by the way?
Andre?
Andre. All right, what am I looking for, Andre? Okay.
0, 0.
I'm looking for 0.005. All right, 1/2 of 1%. All right, is less extreme.
I see.
Negative
0, 0.
2.575.
Yeah, it's in between numbers.
Okay.
2.575.
Yeah, sure. 2.575, or we could take the more extreme z-score, which would be 2.58. Would give us a little extra cushion just to be safe. I suggest you take the more extreme. So, the z-score we're looking for is negative 2.58. All right, let's look on the positive side. And we already know what the positive one's going to be because the normal distribution is identical on both sides. But let's just do it for fun. All right, I heard that. Okay, let's look for the appropriate area below the z-score on the positive side. And what would that be? If 1/2 of 1% is going to be more extreme, it's going to encompass, the z-score less than that is going to encompass some amount of the data, 90 something, 99 something. What's it going to be? Andre?
I was going to say, well, I have 99.995.
99.5, right?
Yeah.
Because 1/2 of 1% is going to be greater
Yeah.
than this area below that z-score. So we are looking for 0.995. Let's look in the center, see if we can find 0.995, put our finger on it. Yes. 2.58. All right. So we've been asked a minute ago, actually it's several minutes ago, we were asked for the 95% confidence interval. And we came up with 60,853 plus or minus 942. Now we want the 99% confidence interval. Whoever was asking us for this data said, well, I want to be 99% sure that that mean, that confidence interval encompasses the true population mean. I want to be 99% confident that that is accurate. So let me do this in a different color. All right, this is 99% confidence. All right, so let's take 60,583 plus or minus. What is the z-score we decided is appropriate? 2.58 times the standard deviation for the sampling distribution of the sample mean. And we decided that was 480. 80.8. All right, so let's crunch out this chunk right here. 2.58 times 480.8. 1,240. 0.46? 1,240. Okay. 1,240. 4?
46.
Okay. Okay. So, our answer to this person who tells us she or he wants a 99% confidence interval, we say the answer is 60,583 plus or minus 1,240.5. So this is a wider confidence interval. We have to give them a wider spread of our estimate. We say, well, if you want me to be 99% sure, then I will tell you that the number is between 1,240 of 60,000. Let's actually write those confidence intervals out. Let's what is that actual number? All right, plus or minus. Someone crank that out for us.
59339.5.
593. Let me stop there.
59. We'll start over.
Okay.
59.
59.
33. 9.5. 9. Go ahead, 9.
9. Okay.
0.5.
All right, that's fine.
Okay, great.
Okay.
And then 61. 823.
61. 823. Okay, so that's 99. Let's go back and notate 95. 95. Okay. What do we get for the 95% confidence interval? Remember, it's 60,583 plus or minus 942. Can someone crank that up for me?
59640.
Okay.
61525.
525. Okay. So, tell you what, I am 95% confident that the true population mean, that the actual population mean, the thing you asked me to find, is between 59,640 and 61,525. I'm 95% confident of that. That's not good enough for you? Fine. I'm 99% confident that the true population mean is between 59,339 and 61,823. So, to be more confident, I need to give you a wider confidence interval. And we calculated these z-scores. The 95% was 1.96. The 99% was 2.58 by looking at the z-table and determining how much area under the curve in any normal distribution, because thankfully we know that random sampling falls into a normal distribution, so we can make those types of assumptions and look at the z-table. You may not enjoy looking at the z-table, but you might be thankful that you can, that someone figured it out. Someone said this is the probability in a normal distribution. All right, is that clear? Everything? Okay, yes, Phil.
I understand how on the negative side you're looking at the two most extreme tails, so that's why we split it up, like 50-50, like you said, 99. We're looking at the two extreme tails, it's half of the 1%. Why do we have to incorporate that 0.05 into the 99% that's just in the middle? Like if we look at that, if we look at the normal distribution graph and it fills in just the area under that curve.
Well, all right. So, suppose.
So there's your 0.05 and there's your 0.05. So then the rest of it's just 99. So why are we doing 99.5? Like we were looking inside the table for 0.995, right?
0.9. We were looking. So, for the 99%, we were looking for 1/2 of 1% on the extreme high end,
Right.
and 1/2 of 1% on the extreme low end.
Right.
So we could.
I get that.
This sample, we could have bumped into a bunch of teachers who make an exorbitant amount of money. And we just so happens our sample of 200 teachers, the computer generated came up with all the really, really well-paid teachers.
Right.
There's a 1/2 of 1% chance of that happening. There's also a 1/2 of 1% chance of, yes.
Right. But what about on not looking at the stream and looking at our 99%? So when we're looking at the positive side of the chart, what was the number we were looking at again? 0.99, and then we added that 1/2 of 1% on top of that.
Yeah, we were looking in the center of the z-table. We were looking at 0.005, which is 1/2 of 1%.
Right.
So this is
the extreme ends.
Yeah, and this was negative 2.58, right?
Right.
And then on the other end, we were looking for 9.995. All right, that is positive 2.58. So we have to go 2.58 standard deviations above the mean, and we know that 99.5% of the data is below that. And maybe your question is, this includes the below, right? All right, this is everything that includes the below. All we're ascertaining now is the 5% above. And you have to keep that straight because you need to subtract off. We could have asked a question. We could make this a different statement. We could say, I'm 99.5% sure that the standard, that everything, that the true population mean is below this.
Right. Got it.
Good question. Okay, all right, so let me tell you where we're going for the rest of the class. We do have some work ahead of us, partially because I want to take some time explaining, partially because I want to give you some time working out problems in class to see if you have any questions. So we will be here for a little while longer, but right now I want to take a break. Let's take 10 minutes, clear the head. What time is it now? It is 8:03. Let's come back at 8:15.
Professor,
Yes, Phil.
I told you last class I would be into the final.
Okay.
I will, because we extended out a week. It's just I'll miss the review.
Okay. All right. Well, the review will be online if you want to watch it. Okay. Fantastic. Yeah. I'll just reset it. Okay. Yeah, that's fine. Don't worry about submitting stuff like that. My concern is that you're through the material. Maybe you can make friends with someone who can set up the settings. It's making sense.
But 75%.
99%. 75%. All right, great, man.
I'm aiming for it.
Excellent.
Thank you.
Yeah, you bet. Okay, well, everything is videotaped, just like communications. You can watch it. We're just going to add another little nuance. We don't know the standard deviation. Just like signed up for my other. You've signed up for this class?
Yeah.
Okay.
What other class?
507.
What?
Well, you showed up in this class today. You showed up in this class today. Have you already taken the intro?
I did circle.
Okay, so you're in the right place.
Yeah, because I know that my counselor wrote to me. I did come to the
Did you
first
email
time.
me? You didn't email me.
No.
Anyway, well, the reason I asked is I marked you as not.
That's exactly what she emailed me about.
Okay.
And she said she sent the letter to the registrar's office to let me enroll.
Perfect.
Okay. Yeah, I apologize about
Yeah, no problem, no
I'm sorry for leaving early.
That's all right, just as long as you're able to get the information.
Okay, thank you so much.
Thank you, man. Okay.
Yeah. I'm so confused on how the capsule's working.
Yeah, me too.
Right now, and I'm like, how does this become a business plan?
Yeah, yeah. I was gonna do a business plan, but somebody told me that it's kind of hard to do. Yeah. I'm doing case studies. I just feel like, all right, right there, so I'm like, but I think a business plan, that's great.
Yeah, but the other one takes a semester. That's starting with 3 semesters long.
Yeah.
Yeah, I need to shut the hell out.
I mean, I still have 2 more courses.
Yeah, I had 2 courses including this one. I only got 1 more after this. It's, it's been kind of rough, but kind of going for that big liver view. I have that multiple spin, and it's an extra piece of my stuff today.
Yeah.
But I'm gonna find a book submitting it. But that's super crazy. It's not that we can try to get that line, but it doesn't mean it shows me after. I think I'm gonna miss the other one by 10 minutes. this yesterday. I think it'll be okay.
Yeah, yeah. I'm on it though, right?
It's interesting, but
So you go regular class or something?
yeah, I haven't used basic accounting class.
Oh,
I
yeah.
had so much trouble in scoring that class.
Yeah.
For the longest time, it's always been like a job starting, so I had 4 semesters I keep looking at it.
What was the major?
I'm done with it. I'm done with that.
Yeah. So you just got it to
And it's the one accounting class that really has a five on it.
Yeah. Oh, you did it?
The regular job is very quick. I just think
What do you do?
they like working in school. So like business plan is more about how to structure an organization, how to structure, how to organize the help desk support models or yeah, it's like it's really difficult because there's no industry definitions of what I actually do. So like there was something I should have read.
Yeah.
It's kind of weird how I got it. So I kind of wrote all about that. There's definitions that's for a hiring agency. And I think I might use this as a baseline. Ultimately, all people in business is what they want. You ever ask anybody what they always say is never enough to but you know, that's what I'm considering. But even Gartner research doesn't even have a straight number of what it should do. It varies between businesses, service support levels, and what people are willing to take. So there's no real. I'll never give you an answer. No matter how much I try to talk to you about it, there's never an answer. That was kind of, I was like, I just bring myself into a dance. And I like really yeah, I got very scared about that.
You people looked at me crazy with this PowerPoint training.
I have no guidance. You have guidance. Yeah, well, let's see. Maybe you'll help me refine something better.
Yeah, they have to keep it at a certain temperature.
No.
No.
How's this feeling, Justin? Justin, how's it feeling? Yeah. I saw a confused look a few minutes ago when I was
I
worried.
was definitely confused trying to understand the Z-source stuff for a little bit.
Okay. Do you have a textbook?
I didn't bring it with me.
Okay, that's fine. Why don't you share with
I
Lewis?
was.
Yeah. And I can
I'll share
donate.
with my neighbor.
Okay, I can donate my textbook because it's easier if you have something to look at.
It was just really more confusing trying to understand how to get the Z-score number, how you got to it. But that last tail end
Yeah.
really brought it home.
Good.
Sure does. You know, it's so funny you say that because I was watching Ryan's stuff. I went to school with you.
All right, let's go ahead and come back together and get started again. As I mentioned, fortunately, we do have some work ahead of us. Those of you who had me in class before, you know I do not unnecessarily keep you until 9:30, but today we will be here pretty close to 9:30, and that's just due to the fact that we've got some basics we need to go over, and I want to explain it slowly, give you a chance to work it out in class. So I've taken a sip of coffee. I can share some with you if you need it. And I will try to be as inspirational as I can as we get through this initial slog. So let's turn back to your textbook and let's try another example. I want you to start working this out on your own and then we'll come back together. Let's look on page 249 and let's do number 23. Let's start with 23A. And I can, let's see, if you don't have a textbook, hopefully you can look next to your neighbor and I can donate this textbook. Okay, so Phil has one, you all have one. Karen and Diana have one. Carlos has a cell phone. Yeah. All right. Texting. All right.
Problem 23.
Yes, 23. Are you got it? You good? You're good? Okay. Do you all have a textbook? You want me to? Here, why don't you take this? Why don't you three? We share that one. Maybe the four of you can like scrunch together.
Yeah.
All right, Emeka, we're doing page 249, 23.
No, maybe not.
Emeka, if you want to open us, scrunch close together. Yes. All right, let's go ahead and come together. Even if you're not done with the problem, let's work it together at this point. So what do we, actually you can just tell me, what do we ask to find in this problem to keep us?
The 90% confidence interval estimate of the mean age of all.
So we're trying to find the mean age of adult moviegoers, and we're trying to find 95% confidence, 90% confidence. All right, so how many people do we sample?
1,000.
All right, so n equals 1,000. All right, what did we get for our sample mean?
39.
39. All right, what else do we know?
Standard deviation of the
9.5.
population.
9.5. Excellent. And we're looking for 90% confidence?
Correct.
90% confidence. Okay, so what do we want to do first? We could find the standard deviation of the sampling distribution of the sample mean. We could do that. Want to do that? All right, so let's find that. All Alright, standard deviation of sampling distribution is 9.5 divided by the square root of 1,000, which is 10, equals, what, 0.95? Is that right? Did I do that right? Yeah? Okay. So we know the standard deviation of the sampling distribution of the sample mean is 0.95, and we know that the average age, our sample mean, is 39. Now we need to know the appropriate z-score for 90%. So
That's not
Yeah.
what?
the standard deviation of the sample. It's 0.3. Oh, it's divided by, instead divided by 31.6. 31.6.
Which gives you 0.30.
0.30. Okay, so 0.3. Thank you. Excellent. All right. So now we need to find the appropriate z-score for 90%. So essentially, we want to encompass 90% of the data. So that means 5% of the data. 5% of the time we get it wrong. It's too high. 5% of the time we get it wrong. It's too low. So we need the appropriate z for those 2 points. So we flip open our z's table, and on the negative side, we're going to look for 0.05. So let's do that. What's the square root of 1,000? Yeah, that's not 10. The square root of 100 is 10. Sorry about that. Alright, so we're on page 568. We're looking at the negative side, and we're looking for 0.005 is going to give us the negative z-score that's going to encompass, that 5% of the data is going to be less than. 5% of the time, our sampling distribution of the sample mean is not going to be accurate. All right, Diana, what do you got?
1.64.
That sounds right to me. Negative 1.65.
Oh, yeah.
And if we were to look at the z-score for the positive side, right, what positive z-score is going to encompass everything but this top 5% of the data, which means everything below it, including, as Phil pointed out, this 5%. So we're looking for the center part of that z-score to say 0.95. Okay. Once we do that, we're going to find a z-score of what, Phil?
1.64.
All right, we'll keep it 1.65. All right, everyone with me there? So we need to take our point estimate of 39 plus or minus 1.65 standard deviations. So let's do that. 39 plus or minus 1.65 times 0.3 equals 39 plus or minus, what's 1.65 times 3? 0.3? 0.495. We could leave it like that, or we could actually write out the confidence intervals. Let's leave it like that. Next question. Part B is the same thing, except it wants an 80% confidence interval, right?
Yeah.
So let's just do that together. I'll change colors. Change to red. Okay. So the only difference now is the z-score. So this was z-score for 90%. 90%. Alright, let's find the z-score for Yeah, let me erase this. All right, this is the answer for 90%. Let's see, 90%. I want to find the z-score for 80%. Z. All right, so what that means is how much area is going to be below the curve of the z-score we're looking for. 10%, exactly. All right, so 10%. All right, there's a 10% chance that we get this one wrong on the low side. And how much are on the high side? Same thing, 10% chance. All right, so we're looking on the z-table on the negative side for what? What's the number in the center that we're looking for?
Negative 1.28.
Yeah, that's the z-score, but what's in the center? What's the center of that big page? Here we were looking for 0.05. Now we're looking for 0.1. Everyone understand that? So, take a look here. So in the center of that page, you're looking for 0.1, right? Where is 0.1? Where is 0.1? It's around there somewhere, around there, around there. See if you can find it.
What's the rule? You know, when, like rounding wise, if you want to take the lower and round
Take-
up, or
You could do either. I like to take the more extreme z-score, the higher on the positive side and the lower on the negative. More extreme. Yes, yeah, I like 1.29. All right, good. So you're looking there. You got it. Fantastic. All right, you found 0.1 somewhere in there. What'd you get?
Well, if you're doing the extreme.
1.29. Okay. 1.29. Fantastic. Negative 1.29. Positive 1.29. All right, so let's add 80% equals 39 plus or minus our sample mean of 39 plus or minus a number of z-scores, number of z's, 1.29 times our standard deviation of 0.3. All right, and what does this equal, this 1.29 times 0.3? 0.387. Okay. So 39 plus or minus 0.387. So, let's see. This number, 0.387, is less than 0.495. Why is that? Why is this 80% confidence interval gives us a smaller margin of error? So if you were to just hear someone give you this data, someone were to say, what are we calculating here? What's the 39? It's online. I lost my place. Age, average age. All right, so one person comes to you and says the average age is 39 with a 0.39 years margin of error. Someone else comes to you and says it's 39 with a 0.49, a half year margin of error. So you might be more inclined to like this person, because this person gave you a smaller margin of error, right? This person seems like they really know what's going on. They're able to get precise answers. But the reason they're getting a precise answer is because they're less confident. They can give you a tighter margin of error when they're less confident. Okay. What did I want to do at this point? Okay. All right. Now, I want to go over one definition. I've been using this term margin of error. We're all familiar with this. This is the margin of error. This is the z-score, the appropriate z-score, times the standard deviation. The standard deviation of the sample mean is sometimes referred to as the standard error. The standard deviation of the sampling distribution of the sample mean is sometimes referred to as the standard error. So, standard error. Standard error. Okay, and this margin of error. Margin of error. All I've really done is I've just thrown one definition at you. The standard deviation of the sampling distribution of the sample mean is sometimes referred to as the standard error. Is that fair? Okay. Let's do a quick example to just ingrain that concept. Let's look at page 251, exercise 7.5.
What was that page again?
251, exercise 7.5. All right, I'll go ahead and we'll do this as a class. I'll just read it. We just want to be clear the difference between standard error and margin of error. So the National Center for Health Statistics reports that the average weight in a sample of U.S. men aged 20 to 74 was 191 pounds. All right, so average weight of these men, 191 pounds. If the sample size is 1,200 and the population standard deviation is 18.2 pounds, calculate A, the standard error of the sampling distribution of the sample mean, and B, the margin of error for a 95% confidence interval of the population mean weights. So, let me make some room here. Alright, so in this case we're looking at average weight. And how many people do we sample? N equals 1,200. 1,200. And what do we get for a sample mean? 191. And what is the population standard deviation? 18.2. All right. So let's begin by constructing the standard deviation for the sampling distribution of the sample mean. Notated this way, standard deviation of the sampling distribution of the sample mean is going to be our population standard deviation of 18.2 divided by the square root of 1,200. All right, what does that come out to?
0.5.
How much, Dan, Rennie?
0.525.
0.525. All right, this is, where'd my red go? Red. Okay, oh, red, thank you. This is standard error. Standard error. Okay, so if someone asks you the definition of standard error, you know it is the standard deviation of the sampling distribution of the sample mean. Next, we need to calculate the margin of error, which is exactly what we've done 5 or 6 times before now, at the 95% level. So, we know that the sample mean is 191. 91 plus or minus, what's the z-score we like for a 95% confidence interval? 1.96. 1.96 times the standard error, 0.525. Okay? So that's going to leave us with 1.9 plus or minus, what is this when we multiply it together? I think it's right in the textbook, actually. 1.09. 1.03. Okay. So plus or minus 1.03. And this is margin of error. Margin of error. Okay. So we know standard error, and we know margin of error. Make sense? Okay. Alrighty. So we've got two exciting concepts left. And they all center around one question. In the examples that we've demonstrated or gone through before, we're able to calculate confidence intervals because we are given the population standard deviation. Now, how do you normally calculate standard deviation for a population? We went over it last time. I showed you the formula.
Swerve it.
Yeah, it's the difference for every sample squared. Yeah. Yes, divided by the total number, and then take the whole square root of that. Okay, so in order to calculate that, we need to know the characteristics of the whole population. We need all the data, right? But we don't have all the data. So in order to calculate the standard deviation, we need all the data. So if we don't know the standard deviation, then we do two things differently. One, we calculate the standard deviation in a way that widens that standard deviation, that makes it a little bit bigger. And two, we use a distribution that is also a little bit wider. So those are the two things we're going to do tonight, two remaining things we have to do tonight. One, what is the larger standard deviation we use? And two, what is the slightly different distribution score that we use? So in terms of the standard deviation that we're going to use, we are going to use the standard deviation from the data. So suppose we take a sample of 30 people. All right, we're going to find the standard deviation of that. We're going to take those 30 numbers, we're going to find the average, and we're going to take the sum of squared differences, and we're going to divide not by 30, but we're going to divide by 30 minus 1, which is going to make that just a little bit bigger. And we're going to call this sample standard deviation little s. So this sigma figure is population, standard div, and the little s is sample, standard div, standard div. Okay, and the formula for that is, and I'm going to have to look at this one. S equals square root of the sum of x 1 minus x bar squared divided by n minus 1. Alright, what this means is very similar to how we constructed population standard deviation. This is each of the samples. We're going to have 30 of these little x's, x1, x2, all the way to x30. And then we have the sample mean, which is the mean of all 30 of those samples. We're going to find the difference. We're going to square it. We're going to add that all up together, and we're going to divide by n minus 1. Now, this is very similar to population standard deviation, except in population standard deviation, we don't divide by n minus 1. We divide by n. So what happens to this number when we divide by n minus 1? It's a little bit bigger. And more so for smaller numbers. So if we only have 5 or 6 in our sample, then if we only have 6 in our sample, instead of dividing by 6, we divide by 5. That has a larger effect on making that number bigger than if we had 100 in our sample. Dividing by 100 versus dividing by 99 is not that much of a difference. The way you'll calculate this is your calculator or Excel. And you could just use the Excel formula for, I think, standard deviation S, standard div S dot S is for the sample standard deviation. So that's the first thing we need to do if we do not know the standard deviation when we're taking these samples. So we're solving the same question. Say we're trying to find the average income in this town, and we do not know the standard deviation of the whole population. We calculate it based on the samples. The second thing we're going to do is we're going to use a different distribution. Instead of using the normal distribution, we're going to use a flattened version of the normal distribution. It's one that's going to give us z-scores that are a little more spread out. It's based on the same principle that things fall into a normal distribution naturally. But mathematicians, statisticians had said, if we don't know the standard deviation of the population, let's add a little extra cushion. And this is called the t-distribution. Before we were calculating the normal distribution with z-scores. Now we are looking at the t-distribution. And the t-distribution, let me write it out like this. We'll call this blue normal distribution, normal, and then I'm going to call this red a t-distribution, t-distribution. So it's a little flatter and a little fatter in the tails. So if we want a confidence interval, we're going to have to go to more extreme edges. Instead of saying we're going to go 1.96 for 95% of the data, for the t-distribution we may have to go to 2.1 or 2.3. Does that make sense? Because it is, I feel so bad about this. It is going to be a little confusing when we crack open the t-distribution in a few minutes. But I don't want you to lose sight of the basic concept, which is the normal distribution. We only have to go to 1.96 standard deviations away from the mean to get 95% of the data. The t-distribution, we're going to have to go a little bit further to 2.1, 2.3. We're going to have a wider margin of error. Okay, so let's do that. All right. The last thing, actually, the one thing I need to go over before we open up the t-distribution is what's called degrees of freedom. I'm not going to explain this too much, other than to say that degrees of freedom in the t-distribution is the number of samples you take minus 1. And if it helps you, you can remember that for the sample standard deviation, we're using an n-1 for our sample size. And for the degrees of freedom on the t-distribution, we're also using an n-1. So with that, let's crack open the t-distribution. We'll go through it slowly. I'll be here for you if you have questions. We'll do a couple examples together. So let's look. It is like a couple of pages further on in the z-distribution. It is the next page. It is page 570. Now, it's set up differently than the z-distribution. In the z-distribution, we're looking for probabilities in the middle section, whereas in the t-distribution, we're actually getting the t-scores in the middle section. So, let's see, does everyone have page 570 open? I'm going to talk through this. So if you look on the left-hand side, you see these degrees of freedom. All right, that is our sample size minus 1. And if you look across the top, you see the right tail areas. And if you look at the top, you can see the area or probability in that right tail. So as we read from left to right across the top, we see that 0.1 means there's a 10% chance of a sample being more extreme than that z-score. If we go to the right one, we see 0.05, which means there's a 5% chance of the data being more extreme. 1 over is a 2.5% chance of the data being more extreme. 1 over is a 1% chance. 1 over is a 0.5% chance of the data being more extreme. What I want to direct your attention to first is the degrees of freedom. So look down the right-hand side. You see degrees of freedom starts at 1, goes up to 10, 20, 30, 120. At the very bottom, you see the degrees of freedom is infinity. So that means we have an infinite number of samples. So say we have a very, very large number of samples. What happens at that point is we don't really need to use the t-distribution. We can go back to using the normal distribution. So take a look at the infinity row on the bottom and cross-reference that with the 0.025 at the top. So right tail area is 0.025. Under the infinity, what is the appropriate t-score if I were to tell you I have a population sample size of infinite samples, and I'm looking for an area in the right tail of 0.025? What is the t-score that you would get in that point? 1.96. Sounds familiar, right? What do we know about 1.96 from the previous examples?
5%.
Gives us a 95% confidence interval because 2.5% of the data is above the 1.96 and 2.5% of the data is below negative 1.596. So keep your eye on that 1.96 and just start to look up the column as we get fewer and fewer degrees of freedom. What happens to the t-score? It's bigger. Remember, as we have fewer and fewer degrees of freedom, which means fewer and fewer samples in our sample, we have to use a wider interval. What do you think? We got through the definition. I'm not going to give you any more new information tonight, but I will go over this and make sure you're comfortable reading the t-distribution table. And the main concept is just what we went over just now. If we were to compare infinite number of samples in our sample size, then it would be exactly the same as the normal distribution. If we wanted a 95% confidence interval, we would use a t-score of 1.96. But as we get fewer and fewer samples, we can be less certain. So because of the uncertainty, because of our smaller sample size, we need to use a wider confidence interval to be 95% confident. So as you look up that column, the t-scores get larger and larger. Okay, take a deep breath there. I'm going to take a deep breath, and we're going to look at some examples. All right. Let's take a look at page 255, exercise 7.6. Okay. Actually, okay. So, reading the t-table and constructing intervals with the t-distribution. All right, so we're going to use the t-table in Appendix A to determine the proper t-value for each of the following cases. 10% of the values in the distribution with 18 degrees of freedom will be greater than what t-score? So 10% of the values in the t-distribution will be greater than what t-score? Okay, so let's draw a picture of what it is asking us. Alright, I'm going to erase this part. So forget about the degrees of freedom for a minute. Just think about what this question is asking us. All right, we've got a t-distribution, which is a little shorter and a little fatter than a normal distribution. And this is asking us for 10%. All right, 10% of the values will be greater than this t. All right, t-score. T-score. Also question mark. All right, so we want what t-score will only 10% of the samples be more extreme than? All right, so let's flip the page back to our t-distribution. All right, so t-distribution. Now we're looking at 18 degrees of freedom. So along the left-hand side, we look down, number 18. All right, and we want the area in the right tail to be 10%, which is the first column. And that gives us a t-score of 1.330. Make sense? All right. Let's do B. Page 255, exercise 7.6, B. 95% of the values in the t-distribution with 20 degrees of freedom will be less than or equal to what? So 95% of the values in the t-distribution with 20. So forget about the degrees of freedom for a minute. Just think 95% of the values will be less than or equal to what? So in this case, let's see. All right, we're looking for, all right, now this, we want this data. We want 95% of the values to have a t-score less extreme than this. Now, if this were a normal distribution, what would the z be? Let's just do that for fun. Z-score. z-score would be what?
1.96.
1.96. Fantastic. But now we're looking for the t-score. Alright, what t-score? How, for this regular z-score, we have to go to 1.96. For the t, random. No, it's going to give us a number, and it's going to be higher than 1.96. So, oh, wait a minute. Did I say that wrong? Yes. Right till it's going to be less. Oh, well, I got that backwards. 95% of the values will be less than. Okay. I got it. So 95% of the values will be less than. So 95% of the values in the t-score will be lower because let's calculate the number first, and then we'll discuss what it means. So we're looking 95% of the values in the t-distribution with 20 degrees of freedom be less than or equal to. So let's look in the back of the book for our t-distribution. And if we want 95% of the values to be less, then that means we need 5% area in the right tail. With 20 degrees of freedom, we look across to the 0.05, and we get 1.725. All right. T-score is equal to 1.725. Okay. I said that backwards a minute ago. So the t-score. So we don't have to go as far. All right, I'm sorry, I'm going to explain this the wrong way, so I'm not going to attempt. Let's move on to the next question, and I'll come back to that one. So if we were looking at example C, 90% of the values of the t-distribution will be in the interval between what and what around the center of the distribution. Let's draw a little picture of that. 90% of the value in this t-distribution, 14 degrees of freedom. We'll leave this up on the board so we can come back to that. All right, so 90%, 14 degrees of freedom. Okay, so this is asking us the question, we want 90% here. So that means there's going to be 5% in the extreme top, 5% in the extreme value, low, and we want the t-score equals. Now I will tell you, it's going to be a plus or minus, because we want a negative t-score and we want a positive t-score. So, let's look in the back of the book. 14 degrees of freedom, and we want 5% in either tail. So, we look at degrees of freedom, we go down to 14, we look at 5%, and we get what? 1.761. Does everyone see that? Okay, and we know we're looking for a plus or minus 1.761 for our t value. Okay, so let's try. All right, yes, I've got 2 exercises. What time are we at? All right, let's see if we can work through 2 exercises as a class. Just get some comfort with that. And we will call that a night. So let's look at page 256, exercise 7.7. All right, so So we're using this t-distribution to build a confidence interval. Suppose, page 256, exercise 7.7. Suppose, in a social media illustration, the sample size had been 5 instead of 50. This was an earlier exercise, but now we have a sample size of 5 people, and the value of the population standard deviation is unknown. So we talked about 2 things we need to do when the population standard deviation is unknown. First is we use a sample standard deviation, which is going to be a little bit bigger. The second thing we do is we use a t-score rather than a z-score. All right, below are the 5 samples. Compute the sample mean and standard deviation S. B, show the 90% confidence interval estimate of the overall campus population mean of social media time. So, solution, in computing the sample mean, we just add everything up and divide by 5. And we get 10 as our mean. It's our sample mean. So, let me get some room here. Actually, I don't even know if I can just talk through it because, well, I'll put it up. So our sample mean equals 10. And we calculate the sample standard deviation. And there's a slight difference in calculating the sample standard deviation. Instead of dividing by n, we divide by n minus 1, which is going to make the sample standard deviation a little bit bigger. Which is going to give us a little more cushion. So once we do that, we come up with a sample standard deviation of 3.16. Now, it's asking us for a 90% confidence interval. 5% in the right tail, 5% in the left tail. In degrees of freedom, of course we know is 5 minus 4. 5 minus 1, which is 4. So, let's look up the appropriate t-score that we need for this problem. So again, we're looking for 90% confidence, so which means there's going to be potentially 5% or there is 5% in the upper tail, 5% in the lower tail. So let's flip back to the t-distribution. Page 570. Now this is a low degree of freedom. There's only 5 samples. So that means the degrees of freedom are 4. And if we want 5% in either tail, what is the t statistic? The t-score that we want? 2.132 is correct. So we're going to do 10 plus or minus 2.132 times our standard deviation of our sample mean. I guess I forgot to do this point. So this is the sample standard deviation, but we still need we still need the standard deviation of the sample mean. We calculate the same way we did in previous examples, which is 3.16 divided by the square root of n. And what is n in this case? 5. That's right. Divided by the square root of 5 equals, I have this calculated, it's 1.41, okay? 1.41. And we know that our t-score we're looking for, we just looked on the table and said with a 90% confidence interval, the appropriate t-score is what? 2.132. All right, so our confidence interval is going to be 10 plus or minus 2.132 times 1.41, which simplifies to 10 plus or minus 3.01. Okay. So what we just did with exercise 7.7 on page 256 is we just did the same type of problem we've done 5 or 6 times before earlier tonight, except in this case, we did not know the population standard deviation. So we made 2 adjustments. We used the sample standard deviation, which is a little bit bigger, and we used the t distribution, which is going to give us a little bit wider of a confidence interval. Remember the 90%, yeah, the 90% would be, yeah, so the 90% for Z, does anyone remember what we came up with for Z? 90% for the Z distribution? 1.65. So for the T distribution, because we don't know the standard deviation, we use is a little bit bigger, 2.1. Okay, very last thing, which is a homework problem. I would like us to do individually / together, is page 256, number 34. Let me read you this problem. A simple random sample of size 3 has produced sample values of 120, 130, and 140. Assume the population distribution is normal. Our job is to first compute the sample average, x bar, and the sample standard deviation, s. Then we want to show the 95% confidence interval of the population mean. So just look at that. I'm not going to make you crunch it out. Just look at it. I want to take a minute before I dive into it, though. Think about how you would solve this problem, how it's slightly different from the examples we did earlier tonight. So first things first, can someone be merciful on us and just tell us, either because you have Excel open or you have a calculator that does this, what is the sample mean and what is the standard deviation? Wait 1 second, let me get some room here. Alright. So the sample mean is what?
130.
120?
30.
30.
Alright, and what is the sample standard deviation?
10.
10. Is that right? It's 10. I guess so. Alright. Makes sense. We've got 3, they're all 10 apart. Okay, so given that, I would like you to spend a couple minutes showing the 95% confidence interval for the population mean. You're going to make a statement that you're 95% confident that the true population mean is between this interval. Let me give you a couple minutes to do that on your own. So I just want you, while we're in class, to just have some practice. let's come back together and finish this one off. So, we know the sample mean is 130. We know the sample standard deviation is 10. We know the number of samples is 3. What's the first thing we want to do to solve this problem? Right, find the standard deviation of the sample mean. I'd encourage you to keep becoming familiar with that language. You've heard me say it over and over again. So standard deviation of the sample mean is going to be calculated by taking the sample mean of 10 divided by the square root of 3. It's going to equal what? How much? 5.78. Fantastic.
7.7.
It was 773, so it's 5.77.
5.77?
Yes.
Excellent. All right. Next question is, what is the appropriate... Well, actually, let me just back up a minute. If you were to see this question on a quiz, or you were doing this research on your own, what distribution would you use? Would you use the Z distribution, the normal distribution, or would you use the T distribution? Use the T. Why do you want to use the T in this case?
Yeah, it's such a small sample size.
Small sample size, yes. And there's another thing. We don't know the population standard deviation. We had to estimate. So, given that, what confidence interval are we looking for here? 95%. Okay, 95% degrees of freedom equals 3 minus 2 equals 1. Wait, no, 3 minus 1. Sorry. 3 minus 1 equals 2. So what is the t-score relevant to us? What did you get under? 4.303. Equals 4.303. Fantastic. So we're going to take our point estimate of 130 plus or minus 4.303 times
5.77.
5.77. All right, and what is this little section going to give us?
24.84.
24.8. So 130 plus or minus 24.8. And just for fun, let's do the confidence interval. What's the lower bound of the confidence interval? 105.2. What's the upper bound of the confidence interval?
154.9.
Okay, so let's verbalize what this tells us. Same thing we did an hour or so ago when we started with the z-scores. How do we explain this to someone? How do we explain this confidence interval? And this is all we're going to do today. Right? I'm going to explain this a few times. Now is the time to just relax and verbalize what you've learned over the past 3 hours. We'll say it a couple different ways, and I'll tell you one slight adjustment I have to the homework in the syllabus, and then we'll go. Is that right?
I have a question. Is it 4.3 or is it 3.1?
Who gets 4.3?
Yeah, I have a question.
4.3?
Under 2.
So where's my text? Okay.
Minus 1.
So we have degrees of freedom. Yeah, degrees of freedom is 2.
Oh, it's 2. Okay, so it's
Yep.
That's right.
Okay, perfect. Okay, so once we've got the answer, how do we verbalize this? What does it mean? I asked you, what is the 3? I guess there's no description. There's no description. So Phil, take a shot.
95% confident that whatever this is, sample mean
use the term. What the words I want to hear? I want to hear that you're 95% confident, and I want to hear true population mean,
Okay.
and also I want to hear the term sample mean. Those are the two things I definitely want to hear. I want to hear you say true population mean, and I also want to hear you say sample mean.
We're 95% confident that the sample mean will represent the true mean between the whatever. Never mind.
Okay. And somebody want to take a shot?
I am.
Diana, can you help us out?
I'd say 95% confident. True population mean is in between 105.2 and 154.8.
Fantastic. We are 95% confident that the true population mean is between 105.2 and 154.8. Try it again, Phil.
Well, you confused me that I need to use sample mean also.
Okay.
Those are like.
Yeah.
Yeah, I get it. Okay, the 95%. I'm 90% confident that the true mean will be between 105.2 and 154.8.
Yes. Yes. What's our confidence level again? 95%?
Yeah.
I'm 95% confident that the true population mean is between 105.2 and 154.8. We've done that in a number of iterations tonight. First, we assumed that we knew the population standard deviation, which allowed us to use the normal distribution and allowed us to be a little more precise, our narrower confidence interval. And then we threw the one thing that you seem to have handled pretty well. I hope my nervousness didn't show as I ventured into this. I was like, "We're getting late. I hope they don't riot when I try to show them a different distribution." But it seems like you all got it. So, because we don't know this population standard deviation, we had to make a couple of adjustments. We had to use the sample standard deviation, which is a little bigger, and we had to use the t-distribution, which is a little flatter and a little wider than normal distribution. And we can make the statement that we are 95% sure, confident, that the true population mean is between 105.2 and 154.8. How do y'all feel? Yes. Okay. I'll be around if you don't rustle yet. I'll be around if you want to ask any questions after class. If you have any concerns, you can email me. I want to mention one adjustment to the homework questions. I will send you an email about this, just in case I forget or in case you get started right away. I eliminated a couple of homework problems from the Class 2 homework problems. These are just recommended problems for you to prepare for the quizzes, but you can not worry about these ones. For Class 2, scratch off number 36, number 46, and number 48. Don't worry about those. You will not be tested over.
32, 36, 48.
No, 36, 46, and 48. Alright, so please go over this material soon. Do not let it vanish from your minds. And call me or email me if you have any questions. Thank you. I will see you all next week.
Just a question, the deliverables. We solved the quizzes on Blackboard.
Solve the quizzes and turn in the Excel problems.
Excel from the quizzes or from the
syllabus.
Class?
Yeah, you see it has Excel exercises. That's what you turn in.
For the next class.
Exactly.
Okay, just the Excel.
You can do it tomorrow. No problem. Show your work.
Did science too? Yeah.
My name on the syllabus roster was actually Eduardo Naranjo.
Okay.
Just, but I'm just so just in case you don't find it. I was not here. Yeah, I registered.
Okay, how the materials do you do?
It felt good. I felt ready. It's a lot easier getting classes.
Oh, I think did you watch the video from last time?
I did not get a chance.
Okay, we can if it helps you.
Okay.
But tonight is a critical night because we just watching the basics and we just all we really want to ingrain this before we make it any more complicated than there's trouble. So
Okay.
I'm glad you feel good about it.
Cool. Great.
Fantastic.
Thank you. I appreciate it. Thank you.
All right, thank you. Yes. Wait, you didn't get that answer?
I did it like I wrote it out and then I got that though. At 24.
Okay, so the sample standard deviation. So standard deviation 10 is the correct answer. We can tell that in a couple of ways. One, just by looking at it. So the average. I don't know. There's something you did wrong there. We could pull it up on Excel right now.
I just want to make sure I'm using my calculator right. It's a little bit weird. So like put the numbers.
Let's see if we can. Control Alt delete. Okay. I'll have the material for those next.
Pretty good. Statistics classes. Oh, okay. Majored economics. A lot of stuff.
Do you have standard deviation on that?
No. I have to like.
I think there's a stats. Like you
I
go to this.
never really messed with like any of the features or anything, so.
For math. Yeah, Excel is up. Take like 5 minutes to log on. Okay. What is it? 120? 130, 140. Okay. Alright, so sample. FC. So equals ST standard div of the sample. That's the one we want. Alright. Equals Boom.
Because I did it how they did in the book. I broke it down like this: x minus x bar.
Good.
So in the AP, it gives me that on this calculator.
That's good.
So that's the way I have to do it. Like it's kind of weird. I have to like write it out.
So it's the math is it's 10 squared. So it's negative 10 squared, which is 100. This is 0, and this is 10 squared, which is also 100. So it's 100 plus 100 is 200.
Yeah.
Divided by 2 is 100. Square root 100 is 10.
So I don't know why I did that. I'll show you how I have to put the calculations. Instead of showing up.
You know, honestly, I'm glad that this is the thing you had a question on, because this is an easily solvable calculator problem. How did the rest of the material feel?
Pretty good. It was just that. It was just like, I just want to make sure my